Thanks for joining us. This is the ESIP, ITNI, and CDI Tech Stack Working Group. Today, we're really pleased to be hosting Mike Mahoney, a graduate researcher from SUNY-ESF. He's developed a R package, TerrainR, that really leverages the APIs that are made available through NGP, the National Map API endpoints. That's in part produced by the NGTalk delivery team. And we're really excited to see kind of a good group of people that are bringing in individuals from NGP, our headquarters organization, as well as NGTalk, my group, which is the National Geospatial Technical Operations Center. We're responsible for the National Map operations, US Topo, NHD, and elevation endpoints, and the data services that serve public needs. If we want to go to the next slide. All right, so we've got Mike. He's a PhD candidate over at SUNY-ESF. He had a tech exchange with us a couple months ago, and we were really intrigued by the work that he was doing to provide these immersive 3D and 2D visualizations that made use and leveraged the NGP data APIs that we have available. And there's kind of a good list of those products that are in use. I'm going to go ahead and go to the next slide. All right, and so the available data sets in TerrainR include the 3D elevation, FAIR DEM, the National Agricultural Imagery Program, the NAPE imagery, NHD products, contours, geonames, NHD plus HR, structures, and transportation. And that's not a total list, but the bulk of the service endpoints that are made available through this package and application. And Mike's going to kind of step us through how you would go about utilizing this package to produce these pretty compelling visualizations and products using a couple lines of R code. I'm going to go to the next slide. I think that's kind of my transition. So I'd really like to present Mike. He's going to go ahead and take over, and we should see his screen in just a little bit.
Awesome.
All right, Mike, thank you.
Great. Thank you so much for the introduction, and thanks everyone for coming today. Let me click into my slides so I can actually advance them. So, as Derek said, my name is Mike Mahoney. I'm a PhD student at the State University of New York College of Environmental Science and Forestry. My research focuses on environmental data visualization as a way to help people reason about large-scale, both spatial and temporal systems. Outside of that work, I have a background in machine learning, remote sensing, and more traditional forest ecology. So for instance, I'm part of a team working to estimate how much forest biomass there is across New York State so that we can calculate carbon storage in forest lands as New York continues towards a net zero carbon future. But the reason I'm here today is to talk more about the visualization components of my work. And so today, I'm going to be talking about TerrainR itself, what it does, how to use it. I'm then also going to talk a little bit about why I think game engines are such an interesting way to try and visualize large-scale spatial data. And then I'm going to finish with a few thoughts on where I see this work going over the next few months and years. So with that said, first things first, what is TerrainR? Well, TerrainR is a new R package that focuses on the retrieval and visualization of spatial data. It can be used to download data to use in analyses, to visualize the outputs of spatial workflows, or the two halves can be combined to download and visualize data for areas within the United States. Importantly, though, is that those two focuses are designed to integrate well with the rest of the R spatial ecosystem. So you can feed the data that TerrainR is downloading from the national map to other R functions for analysis workflows, or you can visualize the outputs from non-TerrainR based analyses in Unity or R itself. The two halves can be used separately or as a cohesive whole. So to start off by talking about the data retrieval side of things, TerrainR provides a standard R-based API to access public domain spatial data for the entire United States, provided by the USGS National Map. And as Derek highlighted a second ago, there's a number of different endpoints which you can download this data from. So things including elevation data and orthoimagery are probably the two most commonly used, but then you can also download base maps including contour lines or watershed boundaries. Now, if you were going to use those APIs directly, you would need to know where on the internet they live, as well as some nuances to the different parameters that different APIs take and different maximum extents they can use, things like that. But TerrainR attempts to smooth over those nuances by providing a single point of entry to download this data directly inside of R. From the user's perspective, you should only need to specify the area of interest you want data for and what types of data you're looking to download. So say, for instance, you have some vector geometry. So here I'm going to read into R a GeoJSON file of campsites that are out in Bryce Canyon National Park out in Utah. And I'm going to read those directly into R as an SF object. So SF in R is the dominant vector geometry object type. It's the implementation of the simple features standard in R. And with any sort of vector geometry SF object, we're able to then visualize that directly inside of R using the ggplot2 library. And so we can look and see, okay, this is a point geometry, here's how it's arranged. If we then decide this is the area we're going to work with, we want to download the data for our campsite area here, we can then take that SF object and pass it directly to the getTiles function from TerrainR in order to download our data. So here I'm specifying that I want to download for the bounding box of my campsite object, elevation data and orthoimagery, which are provided as arguments to services here at a 30-meter pixel resolution. If I want to download things like contour lines, I could just add contours to that services argument. If I want to change the pixel resolution, I can just change the argument value for resolution. And getTiles will then go ahead and hit the APIs for the data products you are requesting. If your area of interest is too large to download all at once, it will break it into separate tiles, download that data, and then return a list of where it saved the downloaded data off to. And so this way you are able to quickly see how many tiles were downloaded, where they were saved to, and programmatically load them into R using the paths that get returned by getTiles. And for a lot of people, this is what TerrainR does. It's an easy standard interface to a number of different national map endpoints. But I personally get a little more excited about the other half of the package, which focuses on visualizing spatial data in both 2D and 3D. So to start off by talking about 2D visualization, R already has a lot of great functionality for plotting 2D data. So if you have single band rasters, for instance, like our elevation data, the raster package in R provides a nice plot method which produces these simple visualizations of our raster surfaces like I have on the left of the slide. If we're trying to visualize multiband images like our orthoimagery, which has a red, green, blue value for each pixel across the surface, we can use raster's plot RGB function to create the same sort of visualization. And now these visualizations both take advantage of R's basic plotting capabilities that come when you install R. And those base plotting capabilities are fantastic to build on top of, but rather complex to use directly. And so a lot of people prefer using the ggplot2 plotting library instead. And if you're only trying to plot things like our elevation raster, a single band raster image, it's easy enough to replicate these visualizations inside of ggplot2. But it's a bit trickier to add multiband images to ggplots if we want to do things like use orthoimagery as a base map for a visualization. And so TerrainR provides a new function, geospatial RGB, to do just that, to add any multiband raster image to a plot. By providing a raster stack or a file that can be read in as a raster stack object in R, you can add whatever image you want, which then interacts with the other data layers in your plot as you might expect. So if we, for instance, want to add our campsites on top of the orthoimagery we've downloaded, we can do that very simply. The spatial arrangement of our orthoimagery and our point geometry gets handled without us having to do anything specific to specify how we want these to arrange with each other, unlike some other features for adding these raster images to plots that R provides. And now you might guess from the name geospatial RGB that this function has been designed with spatial data in mind. And it was, but at the same time, you can actually read in any image as a multiband raster using this function. And so there's a lot of potential for really interesting things using this function, which I think future versions of TerrainR are going to explore a little more fully. And so that's the 2D plotting capabilities that TerrainR provides. And I just want to show off quickly some results from a workshop we held with the Community for Data Integration a few months back, where after about half an hour quick introduction to the TerrainR package, we had people go ahead and download contour data, contour lines base maps for areas of interest and produce the maps that are on the screen right now. And I just think it's really cool seeing the sort of maps that people are able to quickly produce, all entirely inside of R using public data, all expressed as code, so that these are incredibly reproducible, incredibly adaptable. And I get really excited seeing this sort of plotting capability. But I think that the selling point of TerrainR tends to be that 3D tag. And TerrainR is part of a bigger movement to create better tools for 3D visualization of spatial data, both within R and across most other GIS tooling. And I want to highlight that TerrainR is designed to operate well with the other 3D visualization tools popular inside of R. So for instance, the Ray Shader package written by Tyler Morgan Wall produces these beautiful 3D visualizations of spatial data directly inside of R. So this gets visualized entirely inside of R. It opens up as an RGL window inside of an R session without having to bring in any other software, anything like that. And we're able to use the same elevation data and orthoimagery that we downloaded earlier to produce these visualizations. But what TerrainR does, I think, uniquely, is extend these capabilities to take advantage of the Unity 3D video game engine for spatial visualization. And so I want to walk through the process of how we actually create those surfaces inside a video game engine right now. So first things first, we'll have to re-download our data. The other visualizations we've made so far have used our data at a 30-meter pixel resolution. In order to create the surface in Unity, we need a much finer grained surface. And so by default, get tiles will download with a 1 meter pixel length. So we'll re-download our data here. Now, at a 1 meter pixel length, our area of interest is way too big to be downloaded as a single tile from any of the National Map endpoints. So our next step is to use another TerrainR function, merge rasters, to take the tiles that are downloaded by get tiles and turn them into individual files. So here I'll be producing elevation.tiff and orthoimagery.tiff from the tiles downloaded by get tiles. And then we need to transform these rasters into formats that Unity can actually understand. And we do that through use of this function from TerrainR, makeManifest. And what makeManifest will do is take in our spatial inputs and turn them into binary files that Unity is capable of importing. Now, makeManifest spits out a large number of files, including these binary objects that'll be used as an elevation surface, PNG images that'll be used as the image overlay on top of our surfaces, and then also a table and some C# code that will be used to automatically import these into Unity. Unfortunately, my computer is not strong enough to run Zoom and almost anything else at the same time, so I'm not able to do a live demonstration of the import process. It is documented in this vignette importing TerrainR tiles into Unity, available with the package documentation. Right now, you'll have to take me at my word that it is effectively a single button press to actually import all of these files into the Unity engine for visualization. And once you do that, you wind up with a surface that looks like this. And so this surface here, I'm now able to interactively explore using, for instance, my mouse here to pan across the surface and my keyboard to actually interactively explore flying over the area. And this is that same elevation and orthoimagery that we've been using throughout the rest of the presentation. I want to stress, though, that these surfaces can be produced from any data product. You can use any single band raster for elevation, any raster for the overlay. We've been using National Map data just for simplicity, but you can use the outputs from any analysis workflow that you want. And this is our visualization. I think the surface looks great and it's pretty easy to produce, but I do think that the obvious question is then, why involve video game engines at all? Unity here is not capital F free software. It doesn't cost money to use, but it's not permissively licensed like R is. And interacting with game engines for visualization requires a different skill set from the programming we've used to download and process spatial data so far. So why bother? And I think there's a couple of reasons. First off, Unity is incredibly efficient. Uh, it can handle massive landscapes with no problem at all. For instance, this surface here is a 1 meter resolution landscape that goes about 13 kilometers in one direction and 10 kilometers in the other. So there's a total of 130 million individual pixels, each with their own coloration and elevation being rendered here. And I can fly over this surface without my laptop fans kicking on. Unity is able to progressively render terrain at different levels of detail, so it's able to produce these massive high resolution surfaces that are a problem for R-based tools, which have to load all of this data into memory in order to visualize. Second, there's a lot of space to expand beyond static surfaces in Unity. As I mentioned earlier, Unity is primarily used as a video game engine, and as such, it provides a lot of ways for users to actually interact with these landscapes. The landscape is entirely physically rendered, so I can, for instance, add a small script to create a character to walk across the landscape. And that strikes me as a potentially really powerful new way for users to interact with spatial visualizations. So here I'm able to walk across this surface using my keyboard and mouse to navigate. Now, at the moment, adding characters like this does require a little bit of familiarity with the Unity UI, but I'm planning on changing that. In the next few months, I'm hoping to have a function that will automatically create and add characters on top of the world. Similarly, I'm working on ways to plant data-defined forests and buildings on top of this surface directly from R, so that you can visualize more than just terrain. And that's the reason I think that this is such an interesting approach to landscape visualization. There's a lot of potential to use game engines for high-resolution interactive visualizations, but up until now, actually doing this has required a completely different skill set than most other data analysis or visualization workflows. By building out ways to create these visualizations in game engines from R, we can potentially make these tools more useful for scientific communication and improve the types of visualizations teams can actually take advantage of. And so I want to close by talking about where I see this work going. So this image here is a still from a fully rendered interactive landscape that people I work with made over the past summer. So this is a screenshot from the Unity engine. I've had people ask if it's a photo before, and it's actually entirely created by someone working in the Unity engine. It does represent an area out in the Berkshire Mountains of Western Massachusetts, but it was created in order to represent that area, not from data, and not as the actual landscape itself, but just as a representation of it. And these areas we've seen are incredibly powerful to try and introduce people to new areas, to new systems that they haven't experienced before, or even to explain how environmental processes work. We, for instance, are experimenting with using these as a way to communicate about forest management activities to people who are less familiar with concepts like forest succession and things like that, as a way to try and help build public support for sustainable forest management. Now, producing these visualizations that look like this is really difficult. This took a few people most of the summer to produce, which is just not practical for most applications right now. And so we're looking at ways to try and automate as much of this process as possible. TerrainR is the first part of that, creating these landscapes from real world data inside video game engines. And we're hoping to move towards being able to plant forests in areas that trees would realistically exist in ways that maintains realistic spacing, species composition, size distribution, things like that, in order to create systems that feel real to people much faster than we can right now. We're also hoping to do some work investigating the characteristics of these visualizations and how people process these visualizations so that we can understand how useful they can be in order to help people understand new systems and processes that they might not be familiar with. I'll be honest, it's early days for this work yet. We're a long ways away from the automated surfaces that I showed with TerrainR to producing this sort of visualization automatically. But we have some really good momentum, and it's a really exciting place to be right now. And so with that, I want to thank everyone for coming today. I should also mention that the State University of New York has funded this work through their ESF Pathways to Net Zero Carbon initiative. I've included links to the package repo and documentation website in the slides, which are available from mm218.dev/ESIP 2021. And you can find me online at Mike Mahoney 218 on everything, or mm218.dev. Thank you so much.
Wow, that was fantastic, Mike. Really good presentation. Really well put together. Want to kind of open up the floor to questions? Are you okay with time right now, Mike?
Yeah.
Okay. Oh, okay, good. All right. Do we have any questions for Mike? And then Megan, if you can monitor the chat to see if there's anybody.
Yes, I'm not seeing anything at the moment. Feel free to pop your question into the chat or raise your hand, and we're happy to receive your question that way.
So I've got, maybe I'll just kind of start it off with the first question, Mike. All right, questions are starting to come in. All right, Megan, do you want to go ahead and field those?
So,
and then
Mike,
I'll hold off until the end.
Mike, it looks like there's a request for a link to your webpage. Great, thank you for popping that in. Julian Chastain is asking, can I use TerrainR in a Jupyter environment?
So I personally am not familiar with Jupyter. I do almost entirely local dev in RStudio. If it has an R runtime, then you can download National Map data and do the 2D visualization stuff inside of Jupyter. No problem. There's no system requirements there. The Unity side of things do require Unity to be installed on whatever system you're running. So I believe that would be outside of Jupyter itself.
Yeah, and just my experience with that is that you would have to really have a reasonably sized compute instance if you wanted to use that Jupyter notebook. So if you want to do any of that graphics processing, that Unity engine is going to consume a pretty significant amount of compute and memory. So I would recommend that you have let's say an RTX graphics card if you can get one. And then at least 32 gig of memory, and at least a Core i7 8th, 9th gen processor, and then the amount of data that it takes to download, that's also significant. So it's not something that you can generally do just on saying your average RStudio Jupyter notebook page, because they're usually allocated just a small amount of compute and a small amount of mem.
Yeah, I will say especially the tiling process for
any other
splitting.
questions?
Go ahead, Mike.
Oh, just saying the tiling process for splitting large elevation surfaces and so on into multiple files for import into Unity can take quite an amount of CPU. I think anyone who's worked with spatial data can be familiar with how computer destroying it can be to do that sort of processing on large extents.
So on the services front, because you do have a lot of the kind of our NGP and NGTalk theme leads and senior managers, I wanted to know, what would you ask for when you've really made a lot of our services available to this package? When you interact with our services, what are some of those things that you would like to see that either are not available now, or you think could be, or you've used it with other services? So we're just looking for an improvement pathway.
Yeah, I would say the things that I get asked the most are additional abilities to query any individual endpoint. So for instance, I know there was something that a user had asked me if there was a way to specify year of acquisition for NAPE imagery, for instance, which I wasn't familiar with. The other one along these lines that I had seen is, I think, what, oh, I'm on a call with a lot of hydrologists as a forester. This is going to be bad. What level stream, what rank stream, I'm forgetting the official term, when querying stream data from the NHD endpoint. Things along those lines. People were wondering, basically, if there could be more ability to actively query endpoints in that way. Order, thank you.
You got it.
I'm sitting here trying to remember my
it.
one hydrology class from years ago.
and you're just killing the hydrologists that are on the call.
I'm sorry.
So it looks like Eliza is asking
do
a question here about whether it's possible to bring line or point spatial data into Unity and create a tour of the landscape based on those data.
Yeah, let me see real fast if I can find. Here we are. Sorry, I'm trying to pull up an example. So there do exist, we have a preprint out on my GitHub. You can find it at Mike Mahoney 218 VRS 2021. It's a paper that we're presenting at a conference next month, I believe, where we walk through adding additional overlays on top of orthoimagery for, in this case, it's visual resource assessment. So we walk through a viewshed analysis showing effectively which points you can see from this location that we used as an example is John Brooks Lodge in the Adirondacks, and conversely, what points in the Adirondacks are able to see this privately owned lodge inside of the wilderness area there. And so you can see you're able to create these other overlays. So here we have it's a black layer at like 80% translucence to dim orthoimagery that can't see the red point. And then we have the red point added itself. And so inside of TerrainR, we're able to add these things to our surfaces using, there's this function, I believe it's vector to overlay. Yeah, vector to overlay and things like that. The issue with using Unity in this way is that Unity is not natively a GIS. Unity is thinking in terms of image files rather than spatial data. And so what the vector to overlay function effectively does is compress that spatial data. So any sort of relationships that are present in your vector data into a raster format, which can then be saved out as an image to be used as an overlay in this way. And so, yeah, you're able to create these flat lines and points on the surface that way, or potentially, it's more complicated. We're building this way eventually, but I do not have an estimated time for it yet. We think it will be possible to bring in actual objects in the world from spatial data in the future, but not yet on that one. Right now, we only have support for doing it in a flat way.
And then I've got another question that's about the potential for taking this package and the components that are necessary to a cloud-based environment so that you could construct and kind of an on-demand environment for users to come in, select that area. I mean, it would take a little bit more on the automation front for somebody to be able to say upload a shapefile that represents a bounded area or a coordinate bounding box to then run the elevation profile and then render that in Unity and provide that as an output. And I just wanted you to kind of walk through that hypothetical. What would it take to run that render engine in a cloud environment that you were essentially creating a gateway for authorized users to come in and then construct these outputs that you just highlighted?
Yeah. So the challenge in this situation, so most of the work from getting the bounding box specified to downloading the data to tiling it can all be done, since that is all contained entirely within R, you can do that in a cloud environment that has R set up in any format. So no matter how you've got access restricted, no matter how you interface with R in that environment, all of that should work without any other dependencies. The challenge comes in with using Unity itself. So at the moment, interacting with Unity requires, or it can't be run in a headless environment, or rather, you can run Unity in a headless environment.
Okay.
You aren't able to import the tiles in a headless environment yet. That
Really?
is,
Okay.
yeah, that is a piece of work that is scoped for. So the next piece that we're working on for these visualizations is planting data-defined forests, which is, as I was mentioning a second ago, bringing in spatial data as 3D game objects in the world. As part of that, we're going to have functionality that can actually render these scenes in a headless environment. It doesn't exist yet, though, just because it hasn't been a large need yet. Whereas once we're combining these multiple pieces, it makes a little more sense for us to prioritize that. Now, the thing I will say too, though, is once you have created this scene, you aren't able to run a remote session. As far as I'm aware, I might be wrong about this, that you aren't able to run a remote session using the Unity engine. You need to have the files locally on a computer, but you would be able to, if you have some network share with a Unity scene on it, you can then launch Unity on your own computer and access those files remotely or move them accordingly.
Right. And just to kind of clarify that a lot of the functionality that you have built into TerrainR doesn't rely on the Unity engine. That Unity engine is an additional feature that you can do a lot of what you displayed just through the R package and the interaction with the services, right? Okay.
Right. Yeah. Unity is just for the stuff that was the video at the end, effectively.
Yeah. Wow, that was really impressive. That's all that I have for my questions, but it looks like we got a couple more that are coming in. Megan, did you catch that one? Yep.
Yes, so Chris, I believe, is responding to Julian saying we put together a Jupyter notebook this summer that uses R's Raise shader to make 3D terrain visualizations. This notebook hits remote services to retrieve. No. Okay, well, that's a great response, Chris. I'm not sure if you want to unmute and say anything more about that. Or...
Yeah, I was just saying, Julian asked about notebooks, and so we got a similar workflow to what Mike's doing, working in a Jupyter notebook, and it's available on the GitHub. And so it's just, I was just putting it out there for someone to play with. It lacks the Unity pathway, so it doesn't solve that problem.
Oh, hey, would you mind doing a presentation in the near future on the race shader work? This
was done by one of my interns this summer, so I can't speak. I can't claim full technical expertise, but I could see if Nat was interested in presenting it. But here's the direct link to the notebook. I just put it in the chat.
Oh yeah. Okay. All right, Chris. Thank you. It's always neat to see these related projects and other ways to do these visualizations.
Yeah, definitely. I mean, I love the Unity part. That's really cool, and I'd love to learn more about that. Actually, about how to make that work.
Yeah, yeah, absolutely. Yeah, if you can, all of you, if you can, Chris, if you can keep us posted on kind of what's going on the race shader, our side of things, and Mike, definitely, it sounds like you've got a lot of work ahead of you in terms of structures and the ability. I mean, the ability to add trees is something. Are you going to be pulling that from point cloud?
So we are interested specifically in, at least I am, whether my boss is a frequent topic of discussion. No, but I'm personally very interested in the ability to sort of experimentally manipulate these environments that we're creating. And so you can, from LiDAR flights or similar, pull individual tree locations with some degree of accuracy and use that as a way to get accurate locations on the ground for, at the very least, the canopy trees that are actually being actually intercepting returns. I personally am concerned about the understory trees and missing that character from LiDAR returns. But then also, I'm very interested in being able to apply or to create forests for areas that haven't been flown recently enough, or to create forests for areas that don't exist yet. So if you're trying to show, for instance, the after effects of management procedure or 50 years of regeneration after management procedure in a forest, it's a lot easier to work with more traditional inventory methods like fixed plot inventories and so on, where people are actually going out and measuring trees. And if you're measuring a location at the same time, we're looking at ways to go from the sorts of plot measurements you're actually collecting on the ground to predictions of where that forest would be in reality. And so I think that it will be relatively easy to move from LiDAR to this approach as well, so that you can then say experimentally delete rows in a CSV if you're saying, okay, well, we're cutting down all the trees larger than 15-inch diameter or something like that. So you can go through and actually experimentally manipulate it. But my personal focus is more on the actual manual data collection at the moment and turning that into forest to walk through.
Got it. Yep, I understood. All right. Looks like the chat questions are kind of quieting down. Kind of want to give one last opportunity for anyone who has some questions to either enter it in chat or group small enough that if you just want to speak up and ask any questions, or if you have any comments or insights, that would appreciate those too. And I'll let Megan check that, and then
Yeah, I'm not seeing any more questions. Just a comment from Dave that he, as a Python guy, he'd love to see how this can be done in Jupyter via Python as well.
Yeah, which unfortunately I've got nothing for. It's been a few years since I've touched Python myself.
Well, I mean, if we can get that running in a Jupyter environment, we do have the our capabilities there, so that might be something of interest. All right, Megan, do you want to kind of close us out? Mike, thanks so much. Excellent presentation. I really see future opportunities for us to interact. Please keep in touch. Let us know if there's anything that you're seeing in the services that you could see improvements, or any features that you would like to utilize. It would be much appreciated. And let's say in 6 months, as you start to add those additional features, again, it is neat to see this progression from us just kind of getting into just reviewing what you had done to you launching this in CRAN and our OpenSci, and now the road ahead looks really bright.
Yeah, and thank you all so much for coming today, and thanks for having me.
Yeah, and thanks for everyone who attended. We really appreciate you coming in.
Yeah, thanks everyone. We look forward to seeing you on next month's IT&I Tech Dive on October 14th at 3 p.m. Eastern, and topic to be announced soon.
Thank you. Thanks a lot, everybody.